the introduction today. And I would like to start with my thanks to the organizers of this meeting for the kind invitation to be here today and share with all of you this topic on the screen. Also, I would like to thank all of you online attending my talk. It's my pleasure to be here today. So the title of my talk you can see on the screen, but it has to do with the fabrication of polycrystalline thin films, not only the metallic copper, but also copper oxide. So here is my agenda for today. I will comment about the copper oxide, copper 1+, and its use for a small molecule sensor like alcohol, actually ethanol. Then I will show you briefly how is the literature today regarding copper and copper oxide thin films. Then very briefly, I will present you how to produce the copper thin films by thermal evaporation. Then I will present you the copper oxide thin films, how we can step from copper, metallic copper to copper oxide thin films by using the annealing at air atmosphere. Then I will show you the surface morphology of copper oxide thin films. Then I will close my presentation with some conclusions. So the copper oxide, actually, we have two different copper oxide. In one of them, you have a copper 1+, and the other one, the oxidation is copper 2+. So copper 1+ is called cuprite, and copper 2+ is called tellurite. So the copper 1+, which is cuprite, actually is a standard P-type semiconductor, and it can be used to build alcohol gas sensor, in particular ethanol. It is very sensitive and fast and provides fast response. The sensors built based on cuprite. And also it has a very interesting aspect, which is you can integrate in this sensor in portable devices, like for instance, your cell phone. But also it can be incorporated in vehicles, so you can use this as a human breath test, which is a very important point in terms of security for the drivers. So this is a very interesting application of cuprite. So if you look at the literature in the last, let's say, in the last 20 years, 2 decades, on the left-hand side of my slide, you can see the number of publications in the last 2 decades regarding the copper thin film, metallic copper thin film. And what you can see is a impressive increasing of publications. Actually, it roughly triplicates in the last 2 decades, the number of publications, coming from close to 6,000 to 7,000 publications a year. This is extracted from Web of Science. On the right-hand side, you can see the plot regarding the copper oxide thin films, actually cuprite. And again, you can see a very impressive increasing in the number of publications, which shows the interest not only in the basic properties of the copper oxide thin film, but also in the promising applications in cuprite, actually for different kind of devices. And you can see that in the last 20 years, it's about the number of publications about 4 times. So it quadruplicates in the last 2 decades. It reaches today something close to 2,000 publications. So how can we manage to produce copper thin films? One very interesting way and very easy to perform is by using thermal evaporation. On the right-hand side, you can see a detail of the chamber. So we keep the chamber in vacuum, of course, and the interesting elements here, the key elements, are the copper wires. So you connect the copper wires in a high voltage, and then there is evaporation of copper wires in the tungsten film, tungsten filament actually, and then you can make a position of your substrate in a distance from the copper wires. The distance is the parameter Z is the distance, and also away from the center of the deposition area, you can position your substrate in a distance R. So these two parameters here, Z and R, are very important parameters to define actually the thickness of the deposition film, but also it can define the crystalline size inside the thin film. So on the left-hand side, you can see if we name omega as the film thickness, actually omega scales with these two parameters, the R and Z, and roughly it follows this expression. So as you increase the distance from the substrate to the copper wires, and then you decrease the film thickness. Likewise, if you increase the distance R from the center of the axial of your system deposition system, and also you increase the thickness. So this expression is very important. It has been used to actually to fit the experimental data regarding deposition of metallic thin films by thermal evaporation. At the same time, so the crystalline size, this typical crystalline size inside the thin films, actually it scales with the film thickness in such a way that's a power law in this scale. So from this, we can extract actually the mean crystalline size. So the mean crystalline size goes roughly using the same expression. And in our case, in our particular case of copper, given the configuration of our thermal evaporation system and the time we use to build the films, so we can actually fit our data, and we found that the exponent n is about 0.4. So let me show you the data in a plot. So here we perform the deposition of a series of samples. Let's say the distance from the substrate to the copper source runs from 4 centimeter up to 12 centimeter. And here we can see the X-ray diffraction of the copper thin films. So, in all this X-ray diffraction patterns, we perform the heat field refinement, so we can extract the mean size, and we can extract the strength, of course, of these thin films. And then we can plot the mean crystalline size, the data extracted from X-ray diffraction, You can see in the plot on the right-hand side, as a function of Z, the Z parameter is actually the distance from the substrate to the filament where you hold the metallic copper. And then you see that the fitting gives you a exponent close to 0.4. And let me get back to the last. So you may have this D naught, actually D naught equals to roughly about 19 nanometer. So we have a very good fitting of the data actually. So we have control of the thickness of the film and the mean size of the crystallite, the copper crystallite inside the thin film. However, this is just the first step while you're trying to produce thin films of cuprite, so the copper oxide. So we managed to characterize all these copper thin films, and I show you in these two tables here. On the left-hand side, we can extract the crystalline parameter, which is copper actually is cubic phase. So we extract the A parameter, the cell volume, the mean crystalline size, and also we can extract from the fitting of the heat weld fitting, we can extract also the residual strain in this field. So it changes systematically as we change the distance from the substrate to the filament of the chamber. And also you can see that the cell parameter A is very close to the cell parameter of the bulk value for metallic copper, and likewise the volume. And we see that the mean size of the crystallite, it changes systematically as a function of the film thickness. So you see that for 4 centimeters in distance is the thicker thin film, and then the crystallite size, mean crystallite size is about 26 nanometer. When we go to 12 centimeters in distance from the substrate to the filament, so the mean crystalline size decreases from 26 down to about 20 nanometer. And also you can see a systematic change on the residual strain. On the right-hand side, we have a different characterization of these copper thin films. So this table collects actually the resistivity of the copper thin films. And here are the thickness in the nanometer for the films. So we have the square or sheet resistance here, and it shows a systematic variation also. It goes from the thicker thin film, copper thin film, like 0.17, 0.18, and it increases as we come to the thinnest thin film. Likewise, the electroresistivity also changes systematically from 4.6 down to 3.3 to the thinnest. So the thicker thin films, 4.6, and the thinner thin films comes down to 3.3. So now we use this annealing at air atmosphere system where we use to bring our copper thin films. And then we heat up these copper thin films at around 200 Celsius for about 20 hours in air atmosphere. Actually, the metallic copper thin films reacts with the oxygen from the air atmosphere, providing the cuprite. This is the chemical reaction that describes. And then, of course, we want to characterize all the cuprite thin films. Here, On the left-hand side, you can see the X-ray diffraction of all cuprite thin films. And also we perform the Rietveld refinement in all the X-ray diffraction patterns. And then a very important point is that we identify in this process just one phase, just cuprite phase. So we managed to oxidize the copper thin films up to cuprite thin films, but preserving just one phase, which is a very important point as far as production of sensors are concerned. So, and then we have the thickness of all cuprite thin films changing actually systematically. And then we collect in the table on the right-hand side, we can collect some important parameters of the cuprite thin films. So the lattice parameter, you can see very close to the lattice parameter of the bulk cuprite, and the cell volume also very close to the cell volume of bulk cuprite. The mean size of the crystallite, it goes from also changing systematically. It goes from the thinnest film, cuprite thin film, which is related to the copper thin films produced at a distance of 12 centimeters. So we found the mean crystalline size at 8.8 nanometer. It increases systematically up to about 24 nanometers when we have our substrate at 4 centimeters from the copper source. So we collect here also the residual strain. Residual strain you can extract from the fitting of the X-ray diffraction data using the Rietveld refinement. So we can see that there is an increase in the residual strain as we increase the thickness of the copper oxide thin films. So again, we can also extract the lattice strain, and the lattice strain comes in decreasing systematically as we increase the film thickness, and eventually it comes to a negative value for the thicker thin film. So all these samples, not only the metallic copper thin films, but also the copper oxide thin films were completely characterized in terms of morphology and also in terms of electrical and crystal properties. So when you look at the surface morphology, which is a very important aspect for construction of devices. So we look at the surface morphology using the atomic force microscopy. So we look at both, but here I present to you the copper oxide, cuprite surface morphology. So you can see that it comes from 7 nanometer, the thickness, the cuprite oxide thickness of 7 nanometer. It provides a film morphology roughness, the roughness about 7 nanometer. When we go to 144 nanometer, which is the second thickest thin film, so the roughness increases from 7 to 12 nanometer. And then we go to the film thickness of 316 nanometer. So the roughness increases to 13 nanometer. And finally, the film thickness, 434 nanometers in film thickness, we come to roughness of about 35 nanometers. So we have the roughness increasing from about 7 to close to 35 nanometers. And that is a very important aspect as far as the performance of device are concerned. So we can build different devices using different copper oxide thin films. And then the performance of these devices, which have to do with the mechanism of binding of the alcohol molecules to the surface of the copper oxide thin films, and then changing electrical properties like resistivity. And so we can use this parameter as a to quantify the alcohol molecules or small organic molecules anyway. So let me come to my conclusion about this presentation today. The first point is that copper thin films, metallic copper thin films, were successfully fabricated by thermal evaporation. And then once we have copper thin films, metallic, we can change and perform the oxidation of these copper thin films to copper oxide thin films, cupride, and we managed to produce the copper oxide in just one phase, cupride, by using air annealing. And the next point is monophasic copper thin films were produced by thermal evaporation, and likewise monophasic copper oxide thin films were produced by air annealing. And we observed that the copper crystalline size systematically increases or change with the film thickness, and likewise the copper oxide crystalline size also systematically increases with the film thickness. Actually, the copper oxide crystalline size goes in parallel with the metallic copper crystalline size, however, below the values. And finally, the surface roughness of copper oxide also changes systematically and increases with the film thickness. So finally, again, I'd like to thank the organizers of this meeting and for inviting me to be here today and share with you my talk. And so if you have any question, I'll be happy to take the question. Otherwise, you can contact me by my email address in the bottom of this slide. I'll be happy to answer it to you. Thanks again.